So we're going to do a relatively quick lesson for our module 4 overview. And this would be a good one to take some notes on because I'm going to summarize all the formulas we've looked at so far. So the big thing we've looked at here is percent change, which we started looking at way back in the previous course. And percent change comes in two forms. You could end up with a growth rate, or you could end up what we call a decay rate. Like the car depreciation kind of problem. So either way, what we end up with, we call it R for our rate. So that's a variable we see a lot in these problems. If it's a decay rate, then R is going to be some negative number. If it's a growth rate, then R is going to be some positive number. Like with the Ebola outbreak, there was an 80% growth rate. With car depreciation, we saw like an 18% drop in the value of the car every year. Positive rate or negative rate? That's good. So then what we did is based on that growth rate, we built what was called a growth multiplier. And the growth multiplier is where we think about it with respect to 100%. So we always took 1 plus R is what I called it. If R was a positive number, we'd end up with over 100%. If R was a negative number, we'd end up with under 100%. And we ended up multiplying by that over and over again. What does repeated multiplication lead to in math? Powers, right? Yeah, so from here, the growth multiplier led us into these exponential equations. So that was our next stage. So our exponential equations, we were calculating some new amount we called A. That was based on some previous amount or principal value. And then we had to multiply that by, parentheses, 1 plus our growth rate. And since we were always repeatedly multiplying by 1 plus R, we just ended up raising that to a power that we call T. So T was some kind of time frame. If I'm moving too fast, slow me down. Ask the question and just say, slow down, please. Hey, Robert. You have a question on yesterday's stuff? Yeah, so after I do my review, we're going to work on the worksheet. There's a couple worksheets for you, Robert. All right, so some things to note about this right here. P always represented the starting amount, whatever that happened to be. So with that Ebola outbreak, there was initially 130 cases, and then it grew from there. With the car, we started off with maybe an $18,000 car to start with. Or maybe we invested $1,000 in a bank account. R, usually R is some kind of annual rate. And if R is an annual rate, what can you tell me about T for time? It's got to be years. Yeah, time has to be years. So whatever period the rate covers, the variable for time has to cover the same rate. So that's our basic exponential equation right there, given some kind of percent change. And again, remember, R could be a positive number, so we're growing, or R could have been negative, so we take away from 1, right? Like a car is dropping by 18%. Then we'd have 1 minus 0.18. So we'd have a growth rate that drops us down. So just example of a couple of those. The case with Ebola, we had something like 130 times 1.8, because we were growing by 80% per year or per month to the time period. And if we graph something like that, starting at 130, it's going to grow up like that. So we plotted some points, it got crazy. Does anybody remember how crazy the numbers got with Ebola? We got like 170 million cases of Ebola in a very short time. So Ebola probably wasn't growing exponentially. Another example is the car depreciation. And so in that case, we had something like $18,000 was the initial value of the car. And then we lost 18%. So that was 1 minus 0.8, which gave us an 82% change in our multiplier. So that 82 right there represents 1 minus 0.18, an 18% drop in the car's value. And in a situation like that, if we graph it, the car is going to start off at that 18,000, but then it's going to sink in value and curve down that way. So in the case of depreciation, the multiplier, which is also the base in this case, is going to be less than 1. In the case with a growth rate like Ebola, our multiplier, which is the base of the exponential, that base is going to be greater than 1. Because we added something to 100%. So those are our two cases that we're playing around with. So there's lots of cases exponential growth or decay apply to. One is finance. And so we came up with a compound interest formula. And so with compound interest, that same formula got just a little bit more complicated because more things happened each year. So we had some principal, some beginning amount. And then with the rate, we had to adjust the APR to divide by some number we called N. N could have been 12 for months, it could be 365 for days. And the power here would be N times T. So just a reminder about all these things mean here. P is our initial amount. Often called the principal. R is our APR. N is the number of periods per year. So that could be something like 12 for monthly, or 365 for days. And there's other options that could be. It could be 4 for quarterly. And T is going to have to be years because I have the rate in years there. So that was our compound interest formula.
Was the when your power there says NT, is that N over T?
No, it's N times T. I just put it in parentheses to remind us on a calculator we have to put it in parentheses. Even though on paper we don't necessarily write it that way. So this let us calculate new amounts over and over again. What we had a problem with is what if we knew the amount we wanted to target, how do we figure out how long it takes to get there? And it turned out in order to do that, we needed an idea called logarithms. So starting off with something like, I have some base, let's call it b, to a power x, and let's say the answer is y. We'll look at some examples of that in a minute. The trick is that the word logarithm means the same thing as exponent. So the exponent x has to be equal to the log, because log is an exponent. The base is b, so we write that under and next to the g there, and then parentheses, the target value is y. So we started getting good at rewriting exponent problems as log problems, so we could plug them into the calculator. So a couple of examples of this. If I start off with something like 10 to the third power, we all know that's 1,000. What would that look like as a logarithm statement? I want to change black to the blue for this particular one. What should I write first? First, I'll start with the exponent, 3, but then you're right, then I would write log. What's the base here? 10. And then I put a parentheses, and what goes in the parentheses? 1,000. Now, on a calculator, log base 10 is the same as just log. These two mean exactly the same thing. So just double check on your calculator, what is the log of 1,000? So whip out your calculators. Calculator better tell us it's 3. Got okay? 458. You're missing me. Okay, so another example, we looked at a new number that's kind of like pi. Anybody remember what it's called? E. E is approximately, anybody remember that one? 2.7-ish, yeah, it's about 2.7. And like pi, it goes on forever. It doesn't repeat a pattern, but we know a lot of digits of it. Okay? So E turns out to be an important number. So like pi is an important number in a lot of different places. E pops up all over the place. Biology, physics, art, nature, finance, you name it.
Art, how did it end up in art?
That's a long story. I'll tell you some other time. So there is a log base E, but before I write that down, I'm just going to say, suppose we took E and we squared it. So earlier on my calculator, I squared E, and my calculator said it was about 7.3890561, and that's where my calculator ran out of digits. Your calculator might show more digits. So see if your calculator can give you E squared. Give it a try. For those who are on computers, your web browser is a calculator. Just type E raised to the second power, and it should whip out a number for you. Everyone getting about that number from E squared? Yeah. And your digits might look different. Like some calculators might show more. It might be like a 5, 6, 0, 9 something. It just kind of depends on the calculator. Okay, so what I want to do is I want to rewrite that as a logarithm. So what should I write first to make it look like that? The 2 equals, and I'm going to write approximately equals because I had to round there, and it's equal to a log. What's the base of the log have to be? E. And then what's the target of the log? It's 7 point blah, 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 right? So 7.3890561. Now, on a calculator, E is such a prevalent number in different areas of math and science that it gets a special symbol. It's called ln for natural log. And you might say, shouldn't that be NL for natural log? But some French guy came up with this first. We didn't say it backwards. So see if your calculator has an LN button on it. If it does, try to calculate the LN of 7.3890561. If you're on a computer, you can just type it as you see it there in your search, and your browser will probably turn into a calculator and give you an answer. And I bet you're going to get pretty damn close to 2. Like 2 with 9 zeros. Yeah, it's wicked close. Okay. So my emphasis here is just the idea of rewriting an exponent as a logarithm just allows us to solve problems we couldn't solve before. Yours says 2? Yeah, it's close enough to 2. To the best of the calculator's ability of calculating. So I remember the first time I saw logs, they seemed totally foreign to me. They made absolutely no sense. But I could memorize this rule and apply it correctly most of the time. And so that is the main point here. Some other things about logarithms is that a log and an exponent are opposites of each other. So logs and exponents are what we call inverse operations. So that means they cancel each other out when I apply them at the same time. For example, if I take log base 10 of 10 to the power 7, log base 10 and exponent base 10 cancel, and only the 7 remains. What's that? It's just 7. If I take the log of 10 to the 7th, I get 7. They cancel each other out, just like a square root and a square. You take the square root of 7 squared, that's going to give you 7 back, because they cancel each other out. I can go the other way with that too. If I start off with an exponent base and I raise it to a power log with the same base of, let's say, 13, exponent base 10 and log base 10 cancel. So guess what this has to be equal to? Yeah, it's got to be 13. We cancel each other out. I always thought this was a little weirder than that first rule about logs and exponents, but everyone's different. Maybe this part makes more sense to you than the previous page there. In my opinion, I think this idea for us is a little bit more important, but they're kind of 2 ways to say the same thing. With regards to that, in solving equations, that version right there was more important to us. That can be taken one step farther. So we get this rule, I'm going to call it the log exponent rule. And that's if you have any log, and inside that log is a base and a power, maybe 3 to the 19th, the power pops out front. So that's going to be equal to 19 times the log of 3. So what happens here is the power pops out as a multiple. It was a power, now it's a multiple. So just plug this into your calculator and see that you get the same answer for both of these. Try typing log of 3 to the 19th power, hit enter. Try typing 19 times log of 3. And you should find they're both the same number. Without my Google calculator, just to check so I can play with you. So log of 3 raised to the 19th. My Google calculator says it's about 9-ish, 9.065. And if instead I take that 19 and write it as a multiple 19 times, I get exactly the same number. Okay? And that can help us solve problems. So we used that yesterday to solve some problem. We used it the day before to solve some problems. And it's just some rule we have to get used to, just like other rules you get used to over time. All right, 2 more things and we're done with the review. We've done a lot already, huh? So the next one was how to type other logs into a calculator. And so sometimes when we were solving problems, we ended up with things like log base 7 of 50, let's say. The problem is the calculator doesn't have a log base 7 button. It's got a log base 10 button. It's got a log base E button. And the cool thing about this, I can rewrite it in either way. So I could say it's log base 10 of 50 as long as I divide by log base 10 of 7, my old base. And as Daisy pointed out the other day, we can also, instead of using log base 10, we can use the natural log, as long as we use it in the bottom too. So as long as these guys match up, we're okay. And the old base just has to go on the bottom as a log row. So that allowed us to change from one base to any other. So that was another important rule. With me, Emily? All right. So I can just rewrite that in general. Log of any base with a target of, say, y, can be rewritten as log base 10 of y over log base 10 of the old base. And feel free to replace log with natural log. This is also referred to as the change of base formula. All right, one last thing, and we'll hit the rest of activity 4.4. Half-life, which we've been playing with in this section, 4.4. We came up with a formula for that based on a few different problems. And the way it works is the new amount is going to be equal to whatever the starting value, the previous amount. The base is always going to be 0.5 because I'm looking for half of what I had before. And the trick is the exponent. The exponent is always the amount of time that's gone by, but we have to divide that by whatever the half-life time is. So in this formula here, HL is just the time it takes to get half of some amount. So like with caffeine, the half-life was 6.5 hours, so I had T divided by 6.5. With carbon-14, anybody remember what the half-life of carbon-14 was? No, it was huge. It was like 5,000 years, 5,730 years. Yeah, so our power there was T over 5,730. Right, so we just take whatever the time is to cut it in half, and we throw that up there. All right, so that's a summary of everything we've done. We've done a lot in these 4 lessons in the last week and a half. So I thought I'd just give you a quick review of all of it. All right, let's take a look at the worksheet. Emily has a question about the worksheet. Let's start with that. What's up, Emily? Which part?
I couldn't figure out the flash.
Number 5? Okay.
I found the Pluto, but I don't see the sun on the map.
Yeah, okay, so I wanted you guys, so I'm gonna hold off on answering that for now, because I want you to do is check with your neighbors on this. So again, here we have a linear scale. Here we have what's called a logarithmic scale, which is basically a scale based on powers. And so I'm just gonna add that to my board just to give a quick note on it, and then I'll set you guys free to discuss question number 5 and 6. So I'm just gonna rescale this by writing just the power down. All right, so for example, this is 10 squared, so I would label this as a 2. 10 cubed would be 3. 10 to the 4th is 4. And so notice that 2, 3, and 4 are all the same distance apart. So instead of scaling by the actual value, we scale by the power of 10 it has. That's a logarithmic scale. All right, go for it. Take a look at question 5, discuss it with each other. Find a neighbor. Let's see. Daisy, it looks like I'm your neighbor because we don't have Emily online today. So feel free to talk or chat a question. I have my chat box visible. What's up?
I have 2 questions.
Yeah, so the way I did this in my spreadsheet in Costco was touch your pen because I haven't copied it. So here, our T is in thousands of years. So although that's the years, I really want another column for just T. So here T would be 0, there it's 2, there it's 3, there's 6, there's 8. And all we want to do is plug into that formula. So for example, this right here for 82 would just be to take the 0, 6, 1, and raise it to the second power, 10, raise it to the fourth power, 17.
Okay.
Yeah.
And then I just got a question.
Yes.
The text question.
I haven't done that yet.
Okay.
Yeah, I'll talk about that today too, though. Yeah. I'm playing catch up on grading, so I
Totally
haven't,
fine. I just wanted to make sure.
I haven't graded your test corrections yet.
Just make sure.
Boring.
Because you put the power in 0, the power in 0. 0.6 squared. 0.88. That one got me. The average to 2.
Tough question. Well, that's just the amount remaining. So here, if you look up here, the formula gives the fraction of the original amount. So that means you have 0.78 left of the original amount after 2,000 years. That's reasonable. 3 is fine. Yeah, so you can think of that as 78%. Yeah, and so what you should find is as time goes by, that's going to keep shrinking.
This is the actual.
Yeah, so we're not using that formula, that's the half-life formula. That's a different way to come up with this. Okay, so for this problem, we're just applying that formula.
Alright.
Yeah. How's it going, Atlanta? Yes, but you don't need logs here.
Okay.
It's way more straightforward.
Okay.
So, for example, Venus is pretty darn close to 10 squared,
Yeah.
and squared is 100. So if we look back at the table,
For real, probably.
Venus is about 100 million miles.
On your,
So if I just,
Right.
so that number, whatever that comes out to, is the square.
This is.
Yeah, so no logs necessary.
Can
Are you guys, did you find Pluto yet?
you work it out?
What'd you get?
Because I didn't realize this is million. So I got 609.
You get about 5,000 million miles?
Yeah.
That's a bit too far.
So you're
Yeah, right around.
Yeah.
you're getting like 6.
What'd you get, Aaron? You got Pluto? Did you get that one yet?
So what, which one?
And would you write down so far?
This is what.
How's that come out?
6,309.
It's like 10 times too much.
Yeah, I remember.
Oh, yeah.
Check the third.
So it's 8 million.
Yeah, so here's 10 to the third, here's 10 to the fourth,
It's like right.
and it's right in between 3.5 and 4.
What is that? If Neptune's 4,500,
Yeah.
I was 55, but too much.
So Neptune, okay, so that's 10 to the 3.5, right? The next line would be 10 to the 3.6, 3.7, 3.8, 3.9, and 4 would be next, right? So Neptune's just below 10 to the 3.7. So in the calculator, what is 10 to the 3.7?
Oh, I'm checking at this one.
Problem, it says use this scale here. Because Pluto's not even on that chart. We're gonna use the scale here.
This one, this is forward. And this one says. Leverage.
This is a different question. This is about like that.
Yeah, but this one's something about the one.
Yeah, but this one says use the scale above. So I'm putting the scale. Yeah, you can't use the top scale with Pluto.
Okay. I didn't know.
So Alana, what did you get for Pluto?
I got. Well, 5,000.
Really? That seems too high.
This isn't that great.
What did you get, Aaron?
I like 6.
You got like 600?
I got like 6,000.
You got like 6,000 too. Okay, maybe I did it wrong.
Yeah. With the-
All right.
On number 5.
Who else got Pluto?
On number 5.
Yeah.
I got 6,000.
Okay, so maybe I'm totally screwing it up. Okay, let's take a look. I swear I got a smaller number. All right, I'm sorry, Cole. Let's see. So Pluto is right here, right? And according to the scale, if that's 10 to the 3.5, this would be 3.6, 3.7, 3.8, 3.9, and then 4.0. So Pluto is just below 3.8. And so Aaron said, you know, maybe it's about 2.78. 3.78. Oh, maybe I typed a 2 there instead of a 3. That's the problem. Okay, so we just need to calculate what is 10 to the 3.78 on a calculator. I typed 2.78. That's my problem. Yeah, it's pretty close to 3.8. I mean, we're just ballparking this. So it's around 6,000 million miles. What's 1,000 million? A billion, yeah. So Pluto is about 6 billion kilometers away from the sun. So, hang on. So I'm a perfect example of it's okay to make mistakes. Just try it. What's up? Yeah, it's around 6,000.
Okay.
Yeah, we're in the ballpark. Yeah. This is the page number. Yeah, so we want to solve this equation. Can you help with that? So give me a few minutes and we'll come back to that one for everybody, because I'm sure everybody could use that. So I had a question to review, question 4. And so I'll do that in a few minutes after you guys play around with 5 and 6 some more.
Which logarithmic, are we adding to the top one?
The logarithmic scale is the bottom. Yeah, so you want to figure out where would ida sit on there for question 6. You're in question 7, all right.
But there's, it says absolute change. This.
Yeah, so,
Calculate how many
no,
per year.
just given what you're given in number 7, so in 1929, it was at 380, it dropped to 42, what's the absolute change? 338, yeah.
I was just wondering if it wanted to average per year, or if it just.
No,
that's-
no, just for 1929. And then you'll turn that to a relative change, and then do the same thing for 2008. And if you got Pluto and Ida, feel free to turn to the next page about stocks. Let's see if we can finish this sucker up today. Another question? So,
Relative change, is this number divided by the starting?
by the starting point, yeah.
Then you gotta remove decimals as well.
The top one has a linear, a regular scale, and the bottom one has a logarithmic scale.
If they both started out at the same point, why isn't the logarithmic scale show it starts at the higher point?
Because the logarithmic scale is just looking at the power of 10 instead. So kind of like the graphs on the previous page. The numbers are spread out different. Same idea here. Bless you.
7.
Yeah.
Are we taking it from
Yeah.
the base for the base?
Yeah, so first, like, just do 1929 first and don't worry about 2008. So in 1929, I went from 380 to 42, so that's an absolute drop of 338. The relative change would then be the 338 divided by the original amount. And so what'd you get for that?
I haven't done that.
We haven't done it yet. Okay, so you're gonna get a percentage for that. Then after you do that, then move over, okay, see what happened in 2008. Find the absolute change, and take that 6,000 divided by the 14,000, the original amount, see what it comes out as a percent. Just to compare them.
Use 10 the power.
Yeah, so we want to know what power of 10 is the 429.
Is 30 is 1,000 and 2.
Yeah, so what do we use to rewrite this to figure out what the power is? Anybody help out Emily here? How do we solve that problem? 10 to what power is 429? So we can place IDA on that logarithmic scale. We need to know what power of 10 that is. How do we figure that out?
Log.
Yeah, it's a log, right? Yeah, so the log of 429 is the power that we want. Exactly. Rock.
It was 2.3.
Yeah, so we can kind of guess it, but the log allows us to nail it down. Exactly.
Or we have computer lab on our like homework and stuff. 3, 4.
Good question. Yeah, 4.4. Oops, I forgot that. 2.63. Did anybody get the percentages for 1929 and 2008?
What?
What was the percent change in 1929? What's that? 37, 11, nope. It's like 88, 89%. Yeah, so this is about 89%. And that's a drop, right? So these are drops here. And then what was the percent change in 2008? That was more like, yeah, 46%, 47%. So which crash do you think felt worse, the 1929 stock market crash or the 2008 stock market crash? 2008?
No.
Yeah, 1929, that was like devastating. Businessmen were jumping out of their 100th floor window in their trading tower. It was so bad. People were just ruined overnight. It was bad. 2008 was bad, but not quite as bad as 1929. It's the percent change that's the bigger deal there. All right, so a couple more minutes and I'm gonna do, I had a request to look at question number 4 again. Take a look at that. What do you think, Aaron? The last 2 questions. Which graph shows the absolute change better? Yeah, so here, oops, this shows the change of 6,000. Now 300 compared to 6,000 is tiny, which is hiding down here. Yeah, so that shows the absolute change. And then the percent change is shown here. So notice here, that drop doesn't look nearly as bad as this drop right here. Yeah, so here's that 88% drop there versus the 46% drop there. Yeah, so the relative change is better revealed by the the logarithmic graph. Yep, call. That was B, the linear scale, the top graph, where it shows that better. And the percent change is better shown by the logarithmic scale, the second graph. The relative change is the second graph, yeah. All right. Yeah. What's that? The relative change is the bottom graph. All right, so question number 4 had asked, when was the amount of carbon-14, or the fraction of it, going to be equal to 20%? Does that sound right? Which should be 0.2. And there's 2 different ways to do it. If you use the formula they gave us on page 1, they said the formula for A is 0.8861 to the power of T, where T is thousands of years. So if we take that and we set it equal to 20, or sorry, 0.2, how do we get the T alone? We have 2 ways to do it. What's that? Logs, yeah. So the way the worksheet had showed in the previous worksheet was to take the log of each side. And then the trick from there is we have a special rule that says what do you get to do with powers when they're inside of a log? You get to pull them out. Yeah, so this becomes T times the log of 0.8861. And that's still equal to the log of 2/10. And then finally, I can break that multiplication by doing what? Division. Yeah, so T is going to be whatever the division of these 2 is. So take the log of 2/10, divide by the log of 0.8861. What do you get when you do that, Emily? Or do you have an Apple calculator? That makes this 10 times harder. So I'll whip out my calculator here. You definitely want to download a different calculator if you use your phone a lot. So log of 0.2, close parentheses, divide by log of 0.8861. I get about 13,000 years. Because I got to remember T is in thousands. So it looks like T is 13. It's really 13,000. All right, if you finished your worksheet up, feel free to submit it. Otherwise, get it to me next class. Don't forget to look at your homework for 4.4 and take a look at the prep for 4.5. Oh, and then test corrections are due soon. I did post my answers to the test at the end of module 3. You did, yeah, I haven't looked at them yet, but I will.
Did I get these backwards in? That's what I was asking.
Oh,
I was just supposed to look at the graph and then say,
yeah,
or was I
so-
supposed to use the numbers because the numbers say that.
so the absolute change is 6,000 versus 300.
Yeah.
So sit here, if that's 6,000, 300 is going to be pretty damn small. If that's 6,000, that can't be 300 because it's bigger. Okay, so that means the absolute change is the top graph. If we look at the relative change, that's 88% versus 46%. Okay, so if that's 46%, we should see a bigger drop there, but we don't. That's 46%, we should see a bigger drop there. So that means this one shows the relative change. So the bottom graph shows the relative, top graph shows the absolute.
All right.
How's it going, Daisy? Do you have any questions?
You want me on number 8 or 4?
Yeah, one sec. Third. All right, so town. Yeah, you had that started off, right?
I kept getting my.
Yeah, so to do that one there, let me write that on the board here. So this is what, lesson 4.3? So lesson 4.3, number 8. All right, so they say the starting population of the town is 72,000, right? And they say the rate of increase is 8%? Okay, so 8%. 8% as a decimal is 0.08. So for my formula, the new amount is going to be 72,000 times 1 plus 0.08, so 1.08. And then I raise that to the amount of years, t. So that's the formula for how this town is changing. What we want to do is figure out when it's 160,000. So we have to set our formula equal to 160,000 and solve. For t. And it looks like you had started writing that down and then erased it.
Yeah.
Yeah, so then to solve this, and I got to be quick here because we got another class coming in. I'd have to divide by the 72,000 to break the multiplication.
I think I hadn't been adding. Just been adding 2.
You did what?
I hadn't added. I just had 0.
Oh, it's got to be 1.08. Yeah, because we always have to change that to the growth multiplier, which is add the growth rate to 1. Yeah, once you have that, it should work out. So then you get the 1.08 to the t equals whatever that comes out to. I'm just going to cross out some zeros and call it 160 over 72. And then I can change it to a log.
Yeah.
From there. So you're right from there?
Yes.
Okay. Yeah, and you can give me that tomorrow. You don't have to get it to me today.